Okay, so we're going to look at a geometric proof of this famous result for the vector triple product. So the standard way of proving this would just be to use the component-wise definition of the scalar and the vector products, and this involves some quite long, tedious calculations. So unfortunately our geometric proof is also going to be quite long, but I think it's much more interesting along the way, and certainly some of the steps are going to help deepen our understanding of what's really going on with the vector and the scalar products. And also I just love an alternative proof. So here we go. Let's start with what is the vector product of two vectors. So we're working in three-dimensional real space here. So we've got two 3D vectors u and v, their vector product or their cross product. First of all, its length is determined by the magnitude of u and v multiplied by sine of the angle between them. So you'll notice whether we have obtuse or an acute angle, we get the same answer here. And then this is also multiplied by some unit vector, and this unit vector is perpendicular to both u and v. And you can determine whether this is going kind of up or down using something called the right-hand rule. So now that we've got this idea of what the cross product is, we can use this to first of all understand why the formula has this form, so some constant times b minus some other constant times the vector c. So we can think of this as we've got b cross c here, so this vector is going to be perpendicular to both b and c. So if we were to draw a plane which contains b and c, like this, then we think about the normal vector to this plane. Well, a normal vector to this plane is just going to be b cross c. We can draw this in here because it's perpendicular to both b and c, so it's perpendicular to that plane. And if we also were to draw a in, let's imagine a goes here, for example, then this vector a cross b cross c is going to be perpendicular to b cross c. So if we just write this symbolically, we can say a cross b cross c is perpendicular to b cross c, where this symbol just means that they're perpendicular. And if it's perpendicular to the normal to this plane, this means that the vector a cross b cross c is actually going to be contained in this plane. So we can imagine it might go here, for example. But the important thing here is that this vector a cross b cross c is contained in this plane spanned by b and c. So because it's in this plane, if we imagine all of these vectors coming out of the origin here, so b and c are coming out of the origin, so are a, so is b cross c, and so is a cross b cross c. And the whole idea is anything contained in this plane can be written as some linear combination of b and c. We can use these like our coordinate axes within this plane. So then we can immediately say actually that a cross b cross c is going to be of this form. It'll be some multiple of b, so let's say lambda, a scalar multiple of b, plus mu, a different scalar multiple of c, where lambda and mu are some real numbers. So our result now amounts to showing that lambda is going to be a dot c, so we want to show that lambda is a dot c, and we also want to show that mu is negative a dot b. So this is what we're trying to show. But unfortunately you might have noticed already that there's a bit of a problem here in a special case, so this is why the proof might end up being a little bit long, that if actually b and c were parallel to each other, then they wouldn't form a unique plane, so this previous argument wouldn't quite work. So we'll just address this special case very quickly. So if b was parallel to c, so this symbol just means that they're parallel to each other, then we can say that b is going to be equal to some scalar multiple of c, let's say k, where k is some real number. So then our left-hand side here just becomes a cross kc cross c. But then, of course, if you have two parallel vectors and you take the cross product of them, this just gives you 0 because you've got sine of 0 or perhaps sine of 180 degrees. So this is equal to 0 for the left-hand side. And then similarly, the right-hand side, if we calculate this now, replacing b by k times c, we've got kc times a dot c minus c times a dot k times c. But then we can just take out this factor of k here and put it on the outside instead. And you can see now that we've got the exact same thing subtracted from itself. So this would also just be equal to the 0 vector. So this is equal to the right-hand side and this is equal to the left-hand side. So we've seen then that the identity also works in this special case where b and c are parallel. So from now on we can assume that b and c aren't parallel to each other. So we'll just assume now that they're not parallel for the rest of the video. And now we can get quite a nice early win in just by doing the dot product of both sides of this equation with a. So let's see what happens if we were to do a dot the left-hand side, and we know that this is going to be equal to a dot all the stuff on the right-hand side. So now we know that the cross product of A with this vector is certainly going to be perpendicular to A, because it's the cross product of the vector A with something. But then the dot product of A with something that's perpendicular to it, the dot product of two perpendicular vectors is just 0. So the left-hand side just becomes 0. And now the right-hand side, if we were to expand the brackets, we get lambda times A dot B plus mu times A dot C. So this gives us a really nice early win here. We can rearrange this. Let's say lambda times A dot B equals negative mu times A dot C. And then you can see how these two are linked to each other. We just need a second equation now with lambda and mu to be able to solve and find the values of lambda and mu like we're trying to. So unfortunately, getting a second equation is much harder. And to simplify this, we're actually now going to show that we can just work with A, B and C as unit vectors. So the reason for this is, let's imagine that this result holds with unit vectors. So let's imagine we've got U, V and W now, they're all unit vectors. And let's rewrite now, let's say A is going to be some constant times U, so let's say this is RU. We'll say B is going to be S times V, and finally C is T times W. So if this result's true for unit vectors, so if this result is true, then let's think about what this tells us for our non-unit vectors. So we can start with A cross B cross C. So A cross B cross C, we can rewrite A, B and C as RU, SV and TW and just take out all of these scalar multiples. So we've got RST times the triple product U cross V cross W. And then we know that U cross V cross W, just by assumption here, is going to be, so let's keep the RST, then we get it's going to be V times U dot W, just assuming that the result works for unit vectors. And this is take away W times U dot V. But then we can reintroduce the RS and T here, so we can group up the V with S's, we can group up the U with R's, and group up the W's with T's. So let's just write this out to be really clear. So we get SV times, we've got RU dot TW minus TW times RU dot SV. And of course this is just, now SV is B, so we've got B times A dot C from those two terms minus it's C times A dot B. So this would prove our result then if we could show that this works when we've got unit vectors. So now for the rest of the proof we're just going to assume that A, B and C are all unit vectors, because if we can show it in the case that they're all unit vectors, now we've seen this is going to extend to the case where they're not necessarily unit vectors. Now we've just done the dot product of both sides of this equation with A, so let's try doing the dot product of both sides with B. So on the left-hand side, this actually gives us a scalar triple product type expression, B dot A cross this vector B cross C. And on the right-hand side, we've got B dot these terms, which we can expand like expanding brackets. So for the scalar triple product expression, we're actually going to use an identity here, which is that if we have the scalar triple product U dot V cross W like this, so this is the only real result that we're going to use without proof here, so I'll include a link in the description for this, but we can effectively rewrite this as V dot W cross U, so we can just cycle round between U, V and W here. But then we could also switch U and W, so having W cross U versus U cross W, you just get the negative of the other. So this gives us negative V dot U cross W. So we're going to use this identity, and this will give us something quite nice to work with on the left-hand side now. So if we say that our B is U, A is V, and B cross C is W, then our left-hand side is going to become negative A dot B cross W in brackets, sorry, B cross C. So this is our left-hand side now, and the right-hand side, you can see where we're going to get B dot B here when we expand the brackets. Just notice that any vector, the dot product for this with itself is the magnitude squared of that vector. But now, because we're working with unit vectors, this is of course just going to be 1, which is particularly nice. You just get lambda times B dot B, which is just lambda times 1, and plus mu times B dot C. And now we can actually reduce the problem from here to proving a slightly simpler problem. So you see here we've got B cross C. then we're going to introduce this. We'll introduce this as a lemma that if we can prove this in a simpler case where we've got a repeated vector, then we'll be able to get the result to follow from here. So if we just write this as a lemma then, that if we have B cross C like this, then this is going to satisfy our identity that we're trying to show. So you'd have B times B dot C minus C times B dot B. But of course B dot B is just 1 as we've seen before, because we're only interested in working with unit vectors. So if we can show that this lemma is true, then this will allow us to substitute in place of B cross C, we'll be able to substitute in this right hand side. So we'll just see where this takes us now. So assuming this lemma is actually true, we've got negative A dot B times B dot C minus the C vector, and this is equal to lambda plus mu times B dot C. But then we can actually eliminate one of lambda and mu here. You see, we've got an equation involving lambda and mu, and we've already got this equation as well. So we're going to multiply by A dot B on both sides. This is going to get a little bit complicated, but then it'll simplify quite nicely later. So if we multiply by A dot B, we've got A dot B multiplied by negative A dot, in brackets, B times B dot C minus C, and then we've got all these brackets still. And this is equal to lambda times A dot B, which you can see we're now going to be able to replace with negative mu times A dot C, and then we've got plus mu times B dot C, and then we've also had to multiply this by A dot B as well. So now we replace this lambda A dot B by negative mu times A dot C, and we can actually factorise this out. So if we just write this is equal to negative mu times A dot C. Let's factorise the right hand side. If we factor out mu, we've got mu times, we've got this B dot C, A dot B, so we'll write this, we can actually write it as A dot B times B dot C, just to put them in a more sensible order there. And then we've also got minus lambda, effectively here, times, so instead of minus lambda, it's minus A dot C, so minus A dot C. And on the left-hand side, we could expand the bracket a little bit here to try and simplify. So let's actually do some of the dot products there. So we've got A dot B on the left-hand side, and if we do the dot product of A with each of these terms, we're going to get, in the big bracket, negative A dot negative C gives us positive A dot C, and then we're going to get a negative term, so we effectively just do A dot B, and this B dot C is just a scalar, so we just multiply by this B dot C. So we end up with negative A dot B multiplied by B dot C. So then this turns out to be really nice, because you see here A dot B, B dot C minus A dot C, then we've got the effectively just the negative of this, haven't we? Now, so these two terms would actually cancel with each other in a certain case, and then we just get a negative 1 on the left-hand side. So we'd get mu is equal to negative A dot B, which is exactly what we're trying to show here. We're trying to show that mu is negative A dot B, and then it follows from this equation here, just substituting in, that therefore lambda is going to be equal to A dot C. So we've actually proven this then, but this all relies on the fact that this bracket isn't equal to 0, because then you just have 0 equals 0. So unfortunately we gain the extra case here where we also need to consider this case where what if A dot C minus A dot B times B dot C, what if this is equal to 0? So we haven't proven it in this case, and of course we still need to prove this lemma is true as well. So now we'll complete the proof in this case first of all, then we'll return to the case where A dot B is 0, which we picked up earlier where we multiplied by A dot B on both sides of the equation, and then finally we'll prove this lemma. So in this case, if we undo some of the work we might have done earlier, if we take out a factor of A, then we can do the dot product of A and C, and then here where we've got A dot B, the negative of this, we've just got minus B times this scalar B dot C, and this is still equal to 0. And you can see this expression in the bracket is looking similar to the right hand side of our lemma. So if we just introduce a negative sign here, we can rewrite this to make this really clear. We've got B times B dot C minus C, this is still equal to 0, and because it's equal to 0 we don't even really need that negative sign, this still holds. And then we can introduce the left hand side, so we've got A dot B cross b cross c, just using this lemma again, and this is still equal to 0. And now we've got a scalar triple product expression, and we can use this cyclic property again of our scalar triple product. So here we could swap the b cross c and the a. This would introduce a negative sign, and this would give us b cross c, the dot product of this, with b dot a is 0, but we'll just rewrite this as a cross b instead of b cross a, and this would introduce a negative sign, but again it just doesn't matter because it's equal to 0. And this is really cool now because b cross c is perpendicular to a cross b, and b cross c, this is the normal to the plane containing b and c, so we can say this is the normal to, we could perhaps say pi bc, and similarly here we could say this is the normal to the plane containing a and b, we could call this pi AB. So if the normals to these two planes are going to be perpendicular to each other, that means the planes themselves have to be perpendicular if their normals are perpendicular. So this gives us a really nice geometric scenario to work with to extract a bit more information that will help us to actually finish the proof in this special case. So if we've got, let's say this is pi AB, and then let's say this one here is pi BC, the more vertical looking one. First thing we'll notice is that B is actually in the intersection of these two planes, because it's the plane containing B and C, and this is the plane containing A and B, both containing the origin. So we've got B is in the intersection of these. We could say that A is somewhere in this plane containing A and B, and we can also put C somewhere in this plane containing B and C. So now we're going to look at the quantity B cross A. So the quantity B cross A is going to be somewhere in this plane pi BC, just because it's going to be normal to B and A, and these two planes are normal to each other. So we could write it perhaps somewhere down here. We've got this is B cross A is contained in this plane. And things get really interesting now if we do B cross A. So we'll go red for this one. So if we do B cross A in brackets, then this is going to be perpendicular to both B and B cross A, which is contained in this plane pi BC. So this is just going to be a normal to this plane pi BC. And this is really cool because now we've got B cross A, because this is a normal to this plane pi BC. We also know that B cross C is also a normal to this plane. So these two have to be parallel to each other. There is only one normal, really. This is unique up to being a scalar multiple. So B cross A is actually parallel to B cross C, and this information is going to be really useful now in finishing the proof off in this special case. And now we can use this lemma again with an A in place of the C to rewrite this expression as B times B dot A minus A, and this is parallel to B cross C. But if we've got two parallel vectors, instead of just saying one's parallel to the other, we could equivalently say that their cross product is 0. So the cross product of this and B cross C is 0, because the cross product of two parallel vectors is going to be 0. And this is quite nice now, because here we can expand the brackets. So if we expand the brackets, first of all, the B and B dot A is just a scalar, so we can take this onto the very left. So we've got B dot A multiplied by B cross C, so B cross and then in brackets B cross C. So you'll see we'll be able to do the lemma on this term as well in a moment. And then we've also got minus A cross B cross C, and this is all still equal to 0. And now we can take the A cross B cross C onto the right hand side easily enough, and if we apply the lemma as well to this first term, so we've got, and we can also rewrite this B dot A as A dot B just to put them in a more sensible order. So we've got A dot B, and then applying the lemma to this term, this becomes B times B dot C minus the vector C, and then this is equal to A cross B cross C, just taking the A cross B cross C onto the right hand side. And then we could actually expand some of the brackets here on the left hand side, so we'd have B times A dot B multiplied by B dot C, and then minus C times A dot B, and the right hand side still stays unchanged here. And this is starting to look a bit problematic, because we're trying to show this is B times A dot C minus C times A dot B equals the scalar triple product there. But we've got A dot B times B dot C there. But don't forget, we're in this special case where A dot B times B dot C is actually just going to be equal to A dot C. So this term here equals A dot C. And if we were to put this in brackets, we're left with on the left-hand side then b times a dot c minus c times a dot b is indeed equal to the triple product a cross b cross c. And then you can see that we're actually done in this special case. Now we'll move on to the case where a dot b equals 0. And in this case, we can work from the equation lambda times a dot b is negative mu times a dot c. So if we have that a dot b is 0, so the left-hand side is 0, this means that one of these terms on the right-hand side, either mu or a dot c, is going to have to be 0. So if we first of all consider what if a dot c is 0, this means a is perpendicular to c. We've also got that a is perpendicular to b. So if a is perpendicular to both b and c, let's think about what this means. This means that a is going to be parallel to the cross product of b and c. So we've got a is parallel to b cross c, because the cross product of b and c is just a vector which is perpendicular to both b and c, so it has to be parallel to a. And then when we consider a cross b cross c, this is just going to be 0 because a is parallel to b cross c, so the cross product of two parallel vectors is just going to be the 0 vector. And if we think about the right hand side of what we're trying to show, we're trying to show that this is equal to, it'd be b times a dot c minus c times a dot b. And of course here we're in the scenario where both a dot b and a dot c are just equal to 0. So this is 0, this is 0, so this whole expression is also equal to the 0 vector. So we've got that our left-hand side is indeed equal to our intended right-hand side. So this proves the theorem in this case, where we've got a dot b is 0 and a dot c is also 0. But what about when mu is 0? Well, if mu is 0, then we can go back to this expression here, which tells us that a cross b cross c is equal to, it's just going to be lambda times b, because mu is 0. So we've got lambda times b. And then if we do the dot product on both sides with b, we've got b dot, in brackets, a cross b cross c is equal to b dot lambda b. So here we've got another scalar triple product expression where we can switch the a and b. This will introduce a negative sign, and then we'll be able to apply the lemma to the inner term. So we've got negative a dot b cross, in brackets, b cross c. So you see we can use our lemma on this term now. And this is equal to, when we do b dot b, we just get 1 because b is a unit vector, so the magnitude of b. So this is literally just equal to lambda. And then we can apply our lemma, so we get negative a dot, and replacing the inside term with the right-hand side of our lemma, we've got b times b dot c minus c vector, and this is still equal to lambda. Then expanding all the brackets here, we get negative a dot b multiplied by this scalar b dot c, and then negative a dot negative c gives us plus a dot c, and this is equal to lambda still. And of course a dot b is just equal to 0, so we do get indeed that a dot c is equal to lambda, which is one of the equations we're trying to show. And we also want mu to be equal to negative a dot b. Of course here mu is 0, so we've got 0 equals mu, and we also know that 0 is a dot b, so this is also equal to negative a dot b in this scenario. So we can see that the theorem is again proved in this case. So this covers all the cases now where a dot b equals 0, and we're finally ready to prove this lemma. And to prove this, we're going to again start with the fact that the vector triple product of three vectors, where we've got the b cross c here, this is going to be contained within the plane that contains b and c, because it's b cross c is the normal to this plane containing b and c, and then b cross this normal is going to be contained in that plane. So we can rewrite this as being, like how we've got lambda b plus mu c, we'll write this as now sb plus t times c. So it's contained in this plane, just like we saw earlier. And we now want to show that s is equal to b dot c, and we want to show t is negative 1 to prove our lemma. So we could start by taking the dot product of both sides here with b. So where we've got b dot b cross c, we're taking the dot product of b with something which is perpendicular to b, because it's b cross something. So this is just going to be 0 on the left-hand side. So this is 0, and this equals the dot product of all of this with b gives us s, because b dot b is 1, just because it's a unit vector, and we've also got plus t times b dot c. So what we can do is rearrange now So we've got s equals negative t times b dot c. But then we can also use the fact that because b and c are both unit vectors, remember the dot product of these is the magnitude of b times the magnitude of c times cosine of the angle between them. So we could actually just replace all of this by a cos theta. So this will turn out to be useful in a moment. So we've got s is equal to negative t times cos theta. So this is our first equation linking s and t. And now to get our second one, we're going to do c dot both sides of this. So if we've got c dot b cross c like this, you can see we've now got a scalar triple product expression, which we'll be able to rearrange in a moment. And on the right hand side, we've got s times b dot c plus t times c dot c. But remember c dot c, because c is a unit vector, that's just going to be 1. So we just have plus t times 1 effectively there. And now here we can rearrange this. Let's swap the b cross c and the c. So we get a negative b cross c dot product with, and we've got again b cross c now, swapping the c and the b cross c terms there. So this is now just negative of the dot product of a vector with itself. So this is now the negative of b cross c, its magnitude, all squared. And this is equal to s times b dot c plus t. And we can rewrite this. Remember, b dot c is just cos theta. So we've got s times cos theta plus t. And here we can go back to the definition of the cross product as well, which will give us a slightly nicer way of expressing this. So the cross product is going to be the magnitude of b times the magnitude of c times sine theta. But of course the magnitude of b and c are both just 1. So this just turns into negative sine squared theta is equal to, on the right hand side, we've got s times cos theta plus t. So now we're ready to solve these two equations simultaneously for s and t to prove our lemma. And in our second equation, where we've got the negative sine squared theta, we can just use the identity cos squared theta plus sine squared theta is 1 to rewrite this as cos squared theta minus 1. And then we can substitute in negative t cos theta in place of s on the right hand side to get negative t times cos squared theta plus t. And then factoring out t on the right hand side, we've got t times 1 minus cos squared theta, and then this is equal to the negative of 1 minus cos squared theta on the right hand side. You can see that then t is equal to negative 1. This is so long as cos squared theta isn't equal to 1, so cos theta without the square isn't equal to plus or minus 1. So we'll come back to this in a moment. But you can see if t is equal to negative 1, then substituting in here, we just get s is equal to cos theta. And we're trying to show that s is equal to b dot c, but remember what theta is. Theta is the angle between b and c, and b dot c is just equal to the magnitude of b times the magnitude of c, they're both 1, times cos theta. So b dot c, remember, is actually cos theta, and then we've shown that s is indeed equal to b dot c, at least in this case where cos theta isn't plus or minus 1. So we've got t's negative 1, we've got s is b dot c. And if cos theta is plus or minus 1, then we can solve this to find theta, and this tells us that theta is going to be either 0 or 180 degrees. But this is the angle between b and c, so remember this would mean then that either b and c are parallel or they're parallel going in opposite directions. We've already ruled out at the very start the case where b and c are parallel, so we're only interested in proving this lemma where b and c aren't parallel. So the proof was actually complete here because cos theta can't be plus or minus 1 when b and c aren't parallel to each other. So this completes the proof of the lemma, which completes the proof of our theorem. So we can see that this holds then for any vectors a, b and c. And I think this is a really nice proof, even though there's a lot of casework there. I think all of the cases, for example, having b parallel to c or a and b perpendicular, or the scenario with the two perpendicular planes, I think it does make sense to have to consider a separate proof for that case because it's such a different scenario geometrically to the general case.